Hello everyone. Let's follow up on the previous session where we discussed how each token is represented in high-dimensional vector space. And we also did a quick exercise about the same word, which is bank, okay, but have different meaning in a different context, right? I do want to expand on this topic a little bit more. Okay, we can run another exercise. In this exercise, we still have two sentences. He is the king, she is the queen. Okay, other than previous one with the same word, we want to capture the similarity between he minus king and she minus queen. So in this for loop, we get the vector for both he, king, she, and queen. We also do this operation he minus king and she minus queen. We want to capture the similarity between these two vectors. All right. We can just see in the output. We will see the similarity change. In the beginning, at the embedding layer, it's 0.923, but later it just increased a lot, almost to 1. And later it dropped to, at the final layer, dropped to 0.988. Okay, it just shows us that after a sequence go through the transformer layers, it just capture deeper and richer context, even just a single short sentence. All right. When we say we can actually mapping words into vector space in order to capture certain semantic meaning, right? This idea really comes from Google's team, this word to vect project, right? Basically, to use a vector representation of word, this vector capture information about the meaning of the word based on the surrounding words. Okay, as you can imagine, in a high dimensional space, this dimensional size does make a difference, right? In the case of GPT-2, it has this 768 dimensions in this embedding space. However, you can also imagine it's not the longer size, the better performance. You're gonna reach certain limit. For example, you mentioned the quality of word embedding increases with higher dimensionality, but right after a certain point, marginal gain diminishes. Right, you do need to find a sweet spot to make the overall representation work well. Okay, don't mention that this value, this dimension will also contribute proportionally to the computational complexity. All right. When we come back to this notebook, we can do some additional exercise. Maybe this can be something you guys can do. Other than this king and queen exercise, we can even do man to woman as waiter to waitress, as actor to actress. All right, and also dog to dogs, cat to cats, and also bigger, biggest versus smaller, smallest. And this opposition used to know as possible to impossible. And nationalities, Japan to Japanese as Australia to Australian. All right, this can be an exercise you guys can play around. All right, let's quickly come back to this diagram. As we mentioned before, we will only cover the right hand side, the decoder only model like GPT, but it's also good to look at the overall picture about the encoder and decoder altogether. So Hugging Face has this good categorize, help us understand there are multiple types of transformer styles. Okay, encoder only, decoder only, and encoder decoder model. But most of the time we are mainly focused on this decoder only model. Okay, when we look at this, we know that like encoder only like BERT, they designed for this bi-directional context and understand the input very well. So as a result, they are suited for understand the context text such as classification, name entity recognition, and question answering. All right. And in terms of the encoder-decoder model like T5 and BART, they are good at the because they do the sequence-to-sequence task, so it's good at this translation, summarization, and question answering. All right, and finally, the decoder only, like GPT and Llama, right? They have this auto-regressive generation, predict the next token given the previous input. So naturally, it's good at this content generation, sentence completion, write essays, and generate code based on a prompt. Okay, we just noticed based on, for example, based on this survey, they just noticed in this evolutionary tree, we just see a lot more decoder-only models compared with other two types. We do want to explain why that is the case. All right. In fact, we also realized this GPT model or decoder-only model can actually do very well on many other natural language processing tasks, right? Not just described over here on the generation. They can also do well in the classification, Q&A, translation, and summarization, right? Why that is the case, right? Because decoder only, they can do everything so well. Okay, why that's the case? We can see OpenAI's research paper, language model are few short learners. They just explain that I think it's over here. Like GPT model can achieve strong performance on many types of NLP data sets, right? Including translation, Q&A, closed tasks, and several other things, blah, 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 performing very well, okay? In this one, in Google's research, they also show that decoder-only model, they can just, using this free short learning technique, they can just achieve remarkable performance across different types of NLP tasks, which is very impressive, right? So as a result, right, we just notice more and more effort has been put to build this decoder-only model, okay? Because we only have this decoder, right, from the architectural point of view. If we only have decoder, we essentially reducing this architectural complexity, right? This simplicity will also help us effectively train the model on the massive data set and also make this scaling very well, right? We will cover this, but pre-training is taking probably 99% of the overall cost. If you can you can pre-train a very good model with this great general natural language processing capability, right? Then we will get this generalization advantage, right? We only need to invest huge amount of money in the pre-training, and then we do supervised fine-tuning for other specific tasks like summarization and translation, right? That means we no longer need to label massive amount of data set in the pre-training stage, which does make sense in all different ways, right? And when we talk about this scaling well, right? Let's also explore this scaling rules. It's called a scaling law for natural language model introduced by OpenAI. They just explain based on their research how does a model perform based on different factors like model size, the training data size, and the amount of compute used for training. Okay, this kind of has been also been reflected in Google DeepMind's another paper about how to get the best performance based on model size, data size, and compute budget. Okay, they just mentioned in different ways how you can train a model very well in an optimal way, right? But as you can imagine, right? Increase the model size will generally, or increase the parameter will generally increase the capability, same as increase the data size, right? We will just make the model perform better, but you still need to find this sweet spot for these factors, right? Otherwise, you're just wasting resources. For example, you see this figure. It will clearly show that, right? If you just have keep increasing the parameters, it would even increase its training loss, meaning you have potentially overtraining or overfitting, right? You have too much data for a small model, or if you don't have find this sweet spot, then you might also end up getting an undertrained model, right, with too little data with but too many parameters. We kind of see this kind of turning points give us is a diminishing return. It simply means scale a large language model. You cannot just brute force, right? But you need to find this balanced way, right? To find this optimal scaling strategy to make a very good trade-off from engineering point of view. Yeah, thanks for watching. I will see you next time.